If you remember last time, we introduced a very important ether, what was called an epoxide, where we take that ether and we kink it into these three-membered rings. And remember, these three-membered rings are very unstable. They don't like to be bent into that acute bond angle, and they don't like those eclipsed bonds. So that makes them very reactive, and specifically reactions that cause that ring to open up. All right, and so we looked at these reactions, and we're going to kind of continue on that topic. We're going to take a step back, though, and first talk about how we make epoxides. All right, so epoxide synthesis here. All right, we got two ways that we can make epoxides. Both of them are going to be starting with an alkene. So I'm going to use cyclohexene here. Okay, and the first way that we're going to make an epoxide is to take our alkene, to turn it into what's called a halohydrin, and then we're going to promote this intramolecular reaction to create our epoxide. So this is going to be this three-step synthesis here. These halohydrin reactions were ones studied in the first semester of this course, where we're going to take our halogen, so for example bromine, which we know will do these addition reactions with our alkenes, but we're also going to do this in the presence of water, all right? And so what we're going to see is a bromine gets added to one side of that alkene and an alcohol group added to the other. All right. And the next step is we're going to promote this intramolecular interaction under basic conditions to create our epoxide. Okay. When they do this last step here, they like to use, instead of sodium hydroxide, potassium hydroxide. It's a little bit more soluble in ethanol. And so they have this basic organic solution here that they use to help promote that basic reaction. What happens here is actually relatively simple. So we can explain this by looking at our mechanism. All right, I'm going to start out with that halohydrin, and I'm going to react it with my potassium hydroxide. What am I going to do to that potassium? Similar to what I would do if it was a sodium, right? Just another group 1 metal. Get rid of it, and what am I going to replace it with? A negative sign, right? It's going to be replaced by a pair of electrons and a minus sign. Hydroxide is a good nucleophile, and that's what it's going to be doing in this reaction here, but specifically going to be a nucleophile towards a hydrogen, so what we would call a base. All right, so if this is going to play, I'm going to tell you, this is playing the role of the base. What do we think is going to be deprotonated over here on my other reactant? The alcohol group. All right, so let's do that. Let's show this bond explicitly. So we can show our hydroxide deprotonating that alcohol group. All right, and then we're going to look carefully at this intermediate here, and we can even note what our product is going to be. right? That six-membered ring, but now with that epoxide group on there. All right, I'm going to tell you that this next step is an intramolecular reaction, meaning that it's going to have both my nucleophile and my electrophile are in the same molecule here. So, both my nucleophile and my electrophile, what do we think the nucleophilic site is going to be? Which specific atom, or pair of electrons rather, is going to be playing the role of our nucleophile? So not the BR. BR will be playing an important role here, but where's the real electron-dense atom in this molecule? Where's my ton of electron density? Negative charge. The oxygen, right? So my oxygen here with a ton of negative charge is going to be playing the role of my nucleophile. So where's my electrophilic site in this molecule? Right, so not the carbon bonded to the oxygen. That pair of electrons isn't going to come down there. All right, my carbon bonded to my halogen, that's a nice polar bond. And importantly, it also has a good leaving group on there. So it can play the role of my electrophile. With the bromine playing the role of the leaving group. All right, and what do nucleophiles do to electrophiles? Attack. So we're going to have that nucleophilic attack and that leaving group leave all in the same molecule, creating our epoxide. Okay? So that's one way that we can make epoxides by taking an alkene, first turning it into a halohydrin, and then turning it into an epoxide. The other method that we're going to use uses what's called MCPBA, which I don't really care if you know this, but just FYI stands for meta chloro peroxy benzoic acid. All right, we just abbreviate this MCPBA. I'm going to draw the structure here just for fun facts. All right. We can actually figure it out pretty easily based on our name here. So first of all, let's all take a second and convince ourselves that this is benzoic acid. All right, are we all in agreement that this is benzoic acid here? Nothing crazy. Okay, so a peroxy acid, different from a carboxylic acid, doesn't have this COOH, but COOOH. So in order to make a peroxy acid, I'm going to add yet another oxygen on the end here. This is a peroxy acid. And we'll talk a little bit about what these peroxy acids do here in a minute. But let's finish off this structure because this was meta-chloro-peroxybenzoic acid. So I'm going to stick a chloro group where? Carbons 1, 2, or 3? Which one? On that meta position. So this is our MCPBA here. All right, MCPBA also reacts with alkenes. So alkenes are our starting points for epoxides always. We're not going to look at the mechanism for this. You can look it up if you're interested. It's not too crazy, but it's beyond the scope of what I think we need to know here. All right. But suffice it to say that this peroxy acid, and this is actually always what peroxy acids are doing. It's kind of weird. But they take these oxygen here, which is not terribly happy in its oxygen-oxygen single bond, and they insert it in between an existing bond, in this case, an existing carbon-carbon bond. So that oxygen is going to be inserted in the middle of that carbon-carbon bond, creating my epoxide. Okay. We can note we get the same product regardless of which method we use for our epoxide synthesis. We're always taking an alkene and converting it into an epoxide, into that three-membered ether ring. Cool. All right, so now let's take this epoxide that we just made and we're going to react it. All right. We said that we have these nucleophilic ring opening reactions. All right, so let's take our epoxide. I'm going to take a epoxide. Okay, I'm going to react it with this nucleophile here. And an important first step, and we'll see why this is important, but we're going to get in the habit early on here, is to look at this nucleophile and ask ourselves, all right, well, is this reaction occurring under acidic or basic conditions? All right, looking at our nucleophile all by itself, we can tell whether we have an acidic or a basic condition nucleophile. So what do we think for this one here? Acidic or basic conditions? So this is basic conditions. How can I tell it's basic conditions? That negative charge. All right, under basic conditions here, remember that means no strong acids. And what we're going to see is that we shouldn't have any positive charges with our intermediates. All right, but negative charges are allowed, so we can use our good, strong nucleophiles under basic conditions here. All right, I'm going to color these two carbons here, one of them in orange and one of them in green. All right, and which one is my, well, I guess, just to be clear, this is my nucleophile, right? My negative charge here, my nucleophile. Where is the electrophilic site in this epoxide? So specifically one of these carbons here at the base of my epoxide. That's going to be my electrophilic site. And yes, it's going to be the green carbon specifically. Why the green carbon? More accessible. All right, and remember the whole shtick here is that this promotes this ring opening reaction. So this oxygen is playing the role of the leaving group in this reaction here. Now, oxygen, we made a big stink about how it's a bad leaving group, right? It creates an oxygen with a negative charge, which is a strong base. We said bad leaving group, and that is absolutely true. But why is it allowed to happen in this special case here? Why is oxygen allowed to play the role of the leaving group? Well, there's no other option, but it could just not react, right? Like, why does this reaction actually happen? Okay. What did we say about those triangles? Super unstable, right? Because this triangle is like dying to pop open here. It is already under an immense amount of strain. You just got to flick it a little bit for that thing to just pop right open, right? So it wants to open up so badly that that oxygen's like, all right, I'll take the negative charge, okay? So we don't usually see oxygen playing the role of a leaving group, but since we have such an unstable, tiny little ring structure, we're going to see that oxygen leaving group leaving us with that alkoxide base. All right, now I got my nucleophile attached on the other end. All right, and my final step here is I need to create that alcohol group, right? I need to protonate that oxygen. What are we going to use to protonate our oxygen? Water. So water is a common, kind of default, but the problem is, and we might use water. We really might, but it's going to depend on our nucleophile. In this case here, we want them, in a lot of cases, these nucleophiles are not just good nucleophiles, but also good bases, meaning they're just going to steal a proton away from water rather than react with our organic molecule. So remember, we had this very clever thing that we're going to do, is instead of using water, we're going to take our nucleophile and we're going to protonate it. And that is what we'll have in our reaction mixture as our proton donor, right? So if this here is my nucleophile with its negative charge, then this here is my protonated nucleophile. And that can play the role of an acid, of a proton donor. And then I don't lose any of my nucleophile population. In fact, when that step happens, now I'm left with another nucleophile that can go on and react. Oh, that's fine, I read it. Okay. Cool. So that was under basic conditions. All right. We can also have acidic conditions. Under acidic conditions, we should see no strong bases. All right, but let's think about what are, I'm going to grab this same epoxide. But let's think about what our nucleophiles should look like here. Okay, am I going to be able to use something like this hydrogen sulfide ion here under acidic conditions? No, why not? So it's not that. We like reactivity, right? But what does this nucleophile have here that's not allowed under acidic conditions? That charge. Like we said with basic conditions, we shouldn't have any positive charges. Under acidic conditions, we should have no negative charges. And we can note there are some exceptions of things like a bromide ion or a hydrogen sulfate, one of these conjugate bases of our strong acids, which are just terrible bases themselves. But when we're talking about acidic conditions in organic chemistry, we're not talking about like pH 4, like a lemon juice sort of situation. We're talking about like you spill it on yourselves and you take care of it immediately, right? We're talking pH like 0 or something like that, often even negative pHs. Right? We're talking about extreme acidic conditions here. So something negatively charged like this is going to be protonated immediately under those extreme acidic conditions. Unless it's a super terrible base, this thing isn't even a great base, but it's not going to survive at pH 0. So our acidic nucleophiles are going to have to be our neutral nucleophiles. All right, and our neutral nucleophiles tend to be our weak nucleophiles. So then why is this reaction going to occur with these weak nucleophiles? Well, again, we're under acidic conditions, so let's put in a strong acid. We could use something like sulfuric acid. We can also just use hydronium here. All right. And under acidic conditions, what do we think our first step is going to be? I guess just to note, our first step cannot be nucleophilic attack. Right? If I had this as my first step, and I'm telling you it's not, but let's just look at why this is not allowed. All right, I have my nucleophile attached. It's still got those two hydrogens, so it's positively charged. But now my ring opening that occurred, I have this oxide ion here. All right, why isn't this allowed? What do we say about our acidic conditions? I can't have no negative charges. I can't have any strong bases, right? This right here is a strong base. So boom, not allowed to be under acidic conditions. So instead, my first step is not going to be nucleophilic attack. right? So exactly, we're going to play the same game that we played with our alcohols under acidic conditions, and we're going to protonate that oxygen. And when we protonated that oxygen, did we make it a better leaving group or a worse leaving group? A better leaving group, right? Which is why we can get away with using these weak nucleophiles. All right, so now, since I have such a good leaving group here, my nucleophile, even though it's weak, can attack, because I'm going to kick off that super stable leaving group there. And notice that because of that protonation step, when that leaving group leaves, it does not leave as a negatively charged oxide ion. It leaves as a neutral hydroxyl group, a neutral alcohol group. All right, because I had my neutral nucleophile, there's one more step here where I have to deprotonate it, right? Because it was neutral when it formed that new bond, it itself had a positive charge. Remember, our neutral nucleophiles always lose a hydrogen when we react them. In this case, since I generated that water molecule in my first step, that can be my base of my reaction here. All right, depending on your nucleophile, it could also be your nucleophile, but we'll just say that that water created as our base. All right, and so what we've created here is this alcohol with that thiol group as well. We'll actually learn how to name these molecules next week. But for right now, we're just going to leave it at that. And we can kind of note that just like under basic conditions, that thiol, that nucleophile, reacted with that more accessible carbon. All right, my primary carbon as opposed to my secondary carbon. But now I'm going to complicate things. Okay, we're going to talk about acidic conditions and tertiary carbons. All right, I'm going to take another epoxide, but instead of having a primary and secondary carbon, this one's going to have a primary and a tertiary carbon. Okay. What was that first step under acidic conditions again? I'm going to protonate that oxygen. All right. But this thing here, this structure is not really a good way to think about this intermediate with that positive charge on that oxygen there. All right. Instead, and this isn't strictly true, this wouldn't strictly be a resonance structure, but I'm kind of going to want you to think about it like this, so we're going to break our resonance rules here. It turns out that because that's a tertiary carbon, it forms a nice stable carbocation. All right. Now this doesn't really happen instead, and again, it's not quite a real resonance structure, but that's how I want you to think about it. As our true structure here is really a hybrid of these two here, where that oxygen atom is holding a lot of that partial positive charge, and that oxygen-carbon bond has already started to break. All right, so our real structure here is, again, a hybrid of these two. Where that carbon-oxygen bond has started to break already. All right, leaving us with a lot of partial positive charge on that carbon. All right, so because of that, if I have my tertiary epoxide and I react it with a nucleophile under acidic conditions, and again, how could I tell that this was an acidic conditions nucleophile here? Because it's not positive charge, but because it's neutral, right? If it's positively charged, it wouldn't be a nucleophile at all. But yes, so since this is neutral here, when I do my products, all right, now my nucleophile is going to be added to that tertiary carbon. Even though the primary carbon is more accessible, that bond has already started to break, leaving that tertiary carbon with that positive charge density. Right? It's almost carbocation-ish. In fact, that's a great way to think about this. We're going to call this intermediate that we produced carbocation-ish. Which is why our nucleophile attacks at that particular position. Okay, so just to summarize here. All right, our nucleophilic ring opening. Under basic conditions, the only thing that we were considering was that accessibility. So that meant primary carbons were more likely going to get added to than secondary carbons, and those super sterically hindered tertiary carbons are not going to be preferred in those addition reactions. But under acidic conditions, we have that carbocation-ish intermediate and the accessibility argument to worry about. That carbocation-ish intermediate only applied to those tertiary carbons. All right, if it was anything else, then the accessibility argument would win. So that's why tertiary is preferred over primary, but primary is preferred over secondary under acidic conditions. Cool. All right, so now we're going to talk about our stereochemistry of these reactions. All right, and actually this first example that we did is a great one to work with here of forming this epoxide from this alkene. Because I could draw my product like this, but I'm not being very stereospecific. I'm not keeping track of my stereochemistry when I do so. If I was being good, then my bonds pointed off of my ring would either be pointed on dashes and wedges. So let's think about this here for a second. All right, would I be allowed to draw my epoxide? I'm now going to be good and do my stereochemistry of my cyclohexane ring here. Could this be my epoxide structure? All right, why not? What does that wedge mean? That's bonds pointed out at you. What does the dash mean? It's pointed into the page, right? Could these possibly be bonded to the same atom? No, they got to be pointed in the same direction in order for this to work, right? So this is not allowed. I have to have them both on wedges, or I could have them both on dashes. Point being, they got to be pointed in the same direction. All right? So now let's take this alkene. Not an alkene, I'm sorry. Let's take this epoxide. All right, we're going to react it with a nucleophile. I'm going to take this alkoxide ion here. Would I be under acidic conditions or basic conditions with this nucleophile? This would be basic conditions. And again, how can I tell? That negative charge. Okay. So importantly, when that nucleophile attacks, it cannot attack from the same side of where that bond is. Right? If that bond's pointed out of the page, it cannot attack from that same side. It has to attack from the opposite side of that ring, what they call the backside attack. I don't know that they thought it through, but we got our backside attack here, so that new bond is going to have to be pointed in the opposite direction, meaning my nucleophile pointed in the opposite direction of where my epoxide oxygen is pointed. All right, so using cis and trans stereochemistry, which one did we produce? The cis or trans isomer? Opposite side, trans isomer, all right? So, and we specifically produced that trans isomer. There's no way for us to get it to where those two new bonds are pointed in the same direction. They have to be pointed on opposite sides of that ring, all right? If we were being good, we would say, and the enantiomer of this molecule, I tell you on your homework assignment, you can give me one or the other, right? There is the other enantiomer where this is a wedge and this one's a dash. You'll get a mixture of both. But importantly, not all stereoisomers are represented because, again, we don't have any of those cis isomers in there. So we're being good about our stereochemistry with these ring opening reactions. Let's do another example just to practice here. Sorry, that's got to be step 2. Step 1, we'll make our epoxide. Oops. All right, so looking at my alkene here, where is my nucleophile going to be added to, the green or the orange carbon? All right, so first of all, step 1, are we under acidic or basic conditions with this nucleophile? This would have to be acidic conditions. And so then we're going to look, this is a tertiary carbon, and this is a secondary carbon. Which one is preferred under acidic conditions? The tertiary carbon. So that means in my product here, my nucleophile is going to be on that tertiary carbon, where my other carbon will have that OH group from my epoxide. So I'm going to point that OH group. Let me actually not put this methyl group in here yet. I'm going to point that OH group, and I could choose either one. I'm going to choose a wedge. So that means when I draw my new bond to my nucleophile, is it going to be on a dash or a wedge? It's got to be pointed in the opposite direction. And remember, these neutral nucleophiles will lose a hydrogen, so NH2. Am I done? I better count carbons here. What am I missing? That methyl group. Now, importantly, if that methyl group is on that same carbon, it cannot be pointed in that same direction. Oh, whoops, I forgot something very important, which is that OH group down here. Sorry. That was also missing. Okay. But importantly, focusing on that green carbon and its methyl group, if that's going to be attached to that same carbon, it has to be pointed in the opposite direction of that other group, which means that is also going to be on a wedge here. All right, so because we were under acidic conditions, we attacked that tertiary carbon, and we made sure to show that our nucleophile and our alcohol group were pointed in opposite directions. Now, to be clear, you could have switched both of these dashes to wedges and wedges to dashes, and that would also be okay, right? That's the enantiomer of this structure. Either one of those would be okay. So let's just put and enantiomer. All right, so it's easy enough when we're talking about rings. What about for our other alkenes? All right, so I'm going to do this reaction here where I again create my epoxide. And then I again react it with some nucleophile. I'm going to pick, sure, let's do a halide ion. Sodium bromide, or really my bromide here. I lied. That's going to make it too ambiguous. We could do that under acidic or basic conditions. I kind of want to make a point here. So let's pick a basic conditions nucleophile. Or rather, what do we use that nucleophile under? Basic conditions. Yes, okay. So we're under basic conditions here. All right, which means that which one of these two carbons are we going to be substituting, or rather adding to the green or the orange carbon? So now under basic conditions, it's just accessibility, that orange carbon. But we need to be able to show our stereospecific product here. So what we're going to do is we're going to rotate this molecule after this first step into what's called the sawhorse projection. All right? And kind of how we want to imagine it is we have our alkenes, and we're going to flip them on their side and look at them on their side. All right? So then when I make my epoxide in our sawhorse projection, our epoxide will be in the plane of the page. These are my bonds now that are in the plane of the page, which means that these alkyl groups have to be sticking either out of or into the page. All right? And you could, importantly, that means that these two methyl groups, since they're pointed on the same side in my alkene, they have to be pointed on the same side in my sawhorse projection as well. I'm going to put them both on a wedge because, again, I'm kind of imagining that I'm looking at this alkene and then flipping it on its side. That's how I'm looking at this molecule. If you put them both on dashes, that would be fine. But importantly, since they're pointed in the same direction in your alkene, they have to be pointed in the same direction when you rotate that molecule into this sawhorse projection. All right, and then that means that that other group, that ethyl group, has to be pointed on the opposite side. So here's my sawhorse projection of this alkene here. All right, and now we're going to move on to step 2. where we react that thing with our alkoxide ion here. All right, like we said, it's going to attack that orange carbon, but importantly, it can't attack it from the same side of where that ring is. It has to attack it from that opposite side, that backside attack. All right, I guess we can go all the way up here. We can go back to where our product side. So then when I draw my product here, again, I'm going to be in my sawhorse projection. So here's my orange carbon. Here's my green carbon. According to my mechanism here, on that green carbon, where should that hydroxyl group be pointed? Up or down? Whoa. Up or down, that hydroxyl group? Up. All right, I'm going to skip. I'm going to kind of lazy and not do a full mechanism. There would be a protonation step that we would need to do here using the protonated version of our nucleophile. For the sake of time, I'm going to skip that step in our mechanism. I really just wanted to show that backside attack there. So now I have to put in my correct stereochemistry about this bond right here. All right, importantly, my nucleophile on my orange carbon needs to be pointed in the opposite direction. All right, and again, so these are my bonds that are in the plane of the page, these three here. I got to fill in these alkyl groups though. Importantly, nothing happened on that green carbon. So I still have a methyl group pointed down, or pointed out at me rather. And I still have that ethyl group pointed down and into the page. Okay. Importantly, this methyl group, it's not going to change the direction in which it's pointed. It's still going to be pointed out at me, but when that nucleophile attacked, it got moved up into this position here. So this would be how I take my alkene with its particular stereochemistry, and I create my nucleophilic, my ring opening product here. With the correct stereochemistry, using these sawhorse projections. All right, we're going to do one more. I'll try to keep this same thing up here. All right, so everybody take a second, try to draw me the product of this reaction with that proper stereochemistry as well in that sawhorse projection. All right, you can skip this step when you get pretty good at this, but for now, I'm going to show that first step in that sawhorse projection. This time I have a methyl group and an ethyl group pointed in the same direction. and that ethyl group, and that methyl group in the back. All right, and do I have an acidic or basic nucleophile here? Acidic. So which one of these carbons, green or orange? Now our tertiary under acidic conditions are going to be preferred. Okay, so importantly, that orange carbon has that hydroxyl group. It's going to be pointed up. And my nucleophile is going to get attached in that downward position. If I fill in my other bonds here, importantly on that orange oxygen, nothing happened. So I still have that methyl group that's still pointed out of the page and down. All right. What am I going to do to these bonds here? Am I going to change my dashes and wedges? So I don't want to change my dashes and wedges. I'm going to keep this ethyl group on a wedge and this methyl group on a dash. I'm just going to point them in a different direction, right? They just got moved up when that nucleophile attacked. So I still have the ethyl group on a wedge. I still have the methyl group on a dash. All right, but now they're just pointed in the upward direction instead of pointed downward. All right, and this is how I would do my product here with the correct stereochemistry. Again, you would actually get a mixture of this and its enantiomer. So if you switched all of these wedges to dashes and this dash to wedge, that would also be the correct answer. All right, cool. All right, so that's how we can keep track of our stereochemistry with our ring opening reactions. When we're talking about rings, it's a little bit more straightforward. We always get that cis product. When we're talking about our alkenes, we're going to use these sawhorse projections to keep track of our stereochemistry. Break. All right, enjoy your weekend.